Okay, we'll go ahead and get started here. Thanks everybody for joining. My name is Chris. I'm going to be hosting today's webinar. I'm also one of the co-founders of MassDriver, which is a visual developer platform that enables engineers and developers to deploy production-ready infrastructure and applications in minutes. We have other members of the MassDriver team in the chat and Q&A rooms. So if you guys have any questions, go ahead and ask them and they'll get answered for you. Let me turn on my camera. I didn't realize my camera was off. Give me 1 second here. There we go. Is the camera showing now? Uh-oh. Well, we may have to continue this without a camera. My apologies. We'll be able to just go through. As long as you guys can see my slides, we'll be able to progress through this. So today in this webinar, we're going to be investigating, diagnosing, and fixing a lot of the common issues that you'll see arise when you're running applications in Kubernetes. If you'd like to follow along and debug these applications with me, I'm going to post some links into the chat. So this first link is going to be a Git repository repo that has the Helm chart that we're going to be deploying and that we're going to be using throughout this webinar. So that's the main thing you'll need to follow along. Additionally, if you're going to be doing anything in Kubernetes, you're going to need kubectl. That is the Kubernetes command line. I've just sent a link there to kubectl. And the last thing I'm going to send here is a link to install a tool called Helm. Helm is a package manager for Kubernetes, and it's a very common tool for installing applications. We're going to be using Helm to install the applications today. So once you have all three of those applications, you'll be able to follow along. Now, the last thing to note here is that the webinar obviously requires a running Kubernetes cluster. If you don't currently have a running Kubernetes cluster, you can head to massdriver.cloud and we can help you deploy a production-ready Kubernetes cluster in either AWS, GCP, or Azure. These clusters take about 15 minutes to deploy. We can't really make the cloud any faster. So if you don't already have a cluster, go ahead and head there and get one deployed. Unfortunately, you probably won't have it ready by the time that we're getting going here, but this video will be recorded and it will be hosted on YouTube. So you guys should be able to follow along afterwards, and we'll send the link out to everybody in the webinar. So let's go ahead and get started. So let's set some objectives up front for what we're trying to do here. First of all, by the end of this webinar, you should have a basic understanding of a lot of Kubernetes terminology and concepts, particularly with regard to running applications. You should be familiar with most of the common kubectl or the CLI commands for Kubernetes that will allow you to check on the health of applications and resources in your Kubernetes cluster. And you should also be able to perform simple diagnostics and troubleshooting of a lot of the common problems that you'll run into when running applications in Kubernetes. Before we really dive in, let's talk about some terminology because you guys are going to be hearing me use a lot of these terms throughout the webinar. The first one is going to be kubectl. You may have also heard this called kubectl or kubectl. This is the official CLI of Kubernetes. This is what I referenced earlier and had you guys go and install. Helm is the package manager for Kubernetes. You can also use a tool called Kustomize. In this case, we're going to be using Helm. It's very useful for managing application configuration and deploying applications into your cluster. Now, the rest of these are actually specifically Kubernetes terminology. A namespace is essentially a subcluster within your Kubernetes cluster. You can use it for organizing resources. In fact, it's recommended that you kind of keep all of your applications isolated to their own namespace. They also provide a relatively thin layer of security between resources. A lot of Kubernetes RBAC is bounded around namespaces. A pod is the kind of lowest level application representation in Kubernetes. It is one or more containers, and it represents a single application instance. Your actual application may be made up of multiple pods, and that would likely be what a deployment is. A deployment is a logical wrapper around a set of pods, and the deployment can control the pod's lifecycle. So, for example, if a pod dies, the deployment can restart it. If you want more pods, it will add them. If you want less pods, it will remove them. If a new version of the application needs to be released, the deployment will handle the process of launching all of those new pods and terminating the old pods. A service is a logical grouping of pods. This is mostly useful for providing network access. The idea here is that in Kubernetes, pods are ephemeral. Your applications should be like cattle, not pets. The idea is that your pods could die at any point and they could come up on another VM with a completely different name. By using a service, you can put a logical single entity in front of all of your pods, and it has a single DNS name. And so now you have something that doesn't change no matter how much your pods behind it are changing. The last thing is a node. A node is really just a worker machine in your Kubernetes cluster. Think of it like a VM. So now that we have that terminology down, let's jump to the next slide, which is, look, I know there's a lot of content here. However, if there's only a single thing you get out of this entire webinar, it is this slide right here. These are the main commands that you're going to need to be able to debug just about anything in Kubernetes. Probably 90% or more of the problems that you run into, you can identify with just these 5 commands. Now, obviously, kubectl can do way more than this, but you're going to see that almost everything we do is going to be comprised of really just the top 3 commands. The extra credit ones down below, port forward and exec, are kind of higher level commands that are useful for diagnosing very, very specific scenarios. But just kubectl get, kubectl describe, and kubectl logs is going to get you really far. Now, I think it's important to point out here that while Kubernetes is powerful and complex, it can also be intimidating. But the fact that I can boil down almost all of debugging in Kubernetes to just this list of really 3 commands, and with those you can operate the most capable container orchestration platform at a basic level, really shows, in my opinion, the power of Kubernetes and how it allows organizations to adopt it early and grow with their use, and complexity of Kubernetes can grow with the needs of their organization. Now, I'm not going to dig into each of these commands right now. Instead, we're actually just going to go ahead and get started, and you'll see how each of these commands work as we go through and actually start doing a lot of the debugging that we have to for a part of this webinar. So what I'm going to be doing is pulling up a terminal. So if you guys are following along, go ahead and get your terminal up. You should have the GitHub repo for this webinar cloned locally, and that's actually where I'm at right now. You'll see that I'm in the webinar repo. If I ls, you'll see a lot of the files that are in there. We're also going to need a terminal, which I've actually already opened a terminal as well. We're going to be using VS Code, and I have this open. So we're going to be jumping back and forth throughout this terminal throughout this webinar between the terminal and the VS Code window. Let's go ahead and get started. So in your terminal, The first thing that we're going to do is we actually have to install the Helm chart that has all of these applications in it. Now, what's funny is this Helm chart is intended to fail. It's intended to break. So we're going to install a bunch of broken applications, and then we're going to go through the process of debugging them. So the first thing that we actually need to do is cd into the chart repo. Now that we're in the chart repo right here, we can install using Helm. So we're going to run Helm upgrade debug. This debug right here is called the release name. The idea is that with Helm, you might install multiple versions of the same application. For example, if you guys are familiar with Nginx, you might need 3 or 4 different versions of Nginx for different applications. And so each of those would be treated as a separate release. And so in this case, we're only installing this once. So the release name doesn't really matter, but we'll just call it debug. When I say dot, that means install from the local directory right here that we're in. You can also install some remote Helm charts. There's many Helm charts that are hosted remotely. You can install those straight from the command line without downloading them if you want. In this case, we're going to be installing the local Helm chart. We'll do -n debugging. -n here is for namespace. I think you can also do -- namespace. The -n is shorthand. So for this, we're going to be creating a custom namespace specifically to install all of this in. We're going to say -i. This says install if it doesn't already exist. Notice that the Helm command is to upgrade. We're going to be doing -i, which means install it if it's not already there. The reason we're doing it this way is we could just run Helm install first, but that command isn't idempotent. That means we can't run it multiple times. If we ran Helm install and then ran it again, it would error because it's already installed. But by doing Helm upgrade -i, we can run this multiple times. And if it isn't installed, it will install it. If it already is installed, it will simply apply an upgrade to the existing installation. The last thing that we're going to do here is create namespace. This is also a thing for idempotency. What this will do is if the namespace we've specified, which is this debugging, isn't already there, it's going to go ahead and create it for us. So then we hit enter. It's trying. There we go. So it is installed. Now we can actually check on everything running in the cluster and see how it looks. So the next command that we're going to run is, sorry, not Helm. We're going to be jumping over to kubectl. Again, kubectl is the command line. We're going to do get pods, and we're going to say in the namespace debugging, because that's where we installed everything. So this is the first instance that we have of actually running running kubectl get. So you can see what kubectl get does is it will go and check on the resources that are running in the cluster. So in this case, we said kubectl get pods. It's going to go and get all of the pods that are in the debugging namespace. Now, unfortunately, it's a bit of a bloodbath here. If we look down the list, none of these pods is actually running healthy or properly. So we've got one in a CrashLoopBackOff. We've got one that's running, but it's technically not ready. We've got one in an image pullBackOff. We've got another one in a CrashLoopBackOff. We've got some pending pods. Gosh, we got a lot of work here in order for us to fix all of this and clean it up. So actually, the first thing I'm going to do here is I'm noticing this has already been installed previously. This is 84 minutes old. Let me delete this installation, and I'm going to reinstall it. So we're starting from fresh, so that everything here is going to be 0 minutes old instead of 84 minutes old. So you'll actually be able to see how that works. We can just say same thing, Helm, but it's going to be delete, or the name of the release is debug, and the namespace is debugging. So if we do this, it's actually going to delete everything that we had in the cluster right there. it's uninstalled. If I now do a kubectl get pods, you'll see everything is gone. So this is actually how we can clean everything up at the end. So it's now it's deleted. Let's reinstall it, and we're going to be starting from scratch, and we should see everything there just like it was. Kubectl get pods and debugging. Perfect. Now everything is 8 seconds old, but it's still nothing is in good shape. So what we're going to do here is we will start at the very top, and we're just going to work our way down, and we're going to fix every single one of these issues. So the first one we're going to work on is this CrashLoopBackOff. Now, one of the things that you can do with kubectl get is you can use labels to filter down the resources that you want. So right now we just did kubectl get pods in the debugging namespace. We can limit it using labels. Labels are just going to be key value pairs that you can arbitrarily assign. Now, I've already assigned key value pairs to every single one of these applications to make it easy for us to find them. So for this first one, it's going to have a label of app equals CrashLoopBackOff. So if I do kubectl get pod and debugging, and the label is going to be app equals CrashLoopBackOff. Perfect. Now we've limited it to just this one pod that we can investigate and we can dig into. So in this case, we have a CrashLoopBackOff. What does this mean? Well, the crash loop part of it means that that the application is coming up, it's running for usually a very brief amount of time. The pod is crashing, which means it's exiting, and specifically exiting with status 1. And then Kubernetes is restarting it. And then it's just that's happening over and over again. That's the crash loop. It is in a loop of crashing and being restarted. The back off is something that Kubernetes actually does for you. It will slowly start adding more and more time between retries. And the idea is, if your application has crashed, 2, 3, 4, 5 times in a row, it's very unlikely that the next time it's suddenly going to start working. And so instead of just trying over and over again rapidly and causing a lot of thrashing of your pods, it's just going to slowly add more and more delay between each of these retries, up to about 5 minutes, which I think is actually configurable as well. And so at the top end, it'll wait 5 minutes before it even retries running your application again. In this case, we've already retried three times, and the last time was 31 seconds ago. So in the event that you have an application that is crashing like this, it is very unlikely that it's actually something wrong with the Kubernetes cluster itself. It's almost always that something is wrong with the container that you're running, with the application itself. In that case, the best thing that we can do is actually check the logs of the application to see if we can get any hints. So let's do that. We can do kubectl logs. Again, we're scoping everything to the debugging namespace because that's where all of our stuff is running. And we're going to say scope it again to the application or to the pod where the app label is CrashLoopBackOff. There we go. So we have some logs, and the good news is we have an error that comes up immediately in our logs. Now, you may be able to tell from this error log that we're trying to run a Postgres container, and it's failing because I specifically use this container because I've run into this situation before, actually multiple times. And that is that in order to start up the Postgres container, you have to set the Postgres password environment variable. And so that's exactly what it's complaining about right here, that we need to specify that environment variable. Luckily, specifying environment variables is very easy. So let's jump over to our terminal. We're going to add that Postgres password environment variable, and we'll redeploy and we'll see if that fixes it. So let's jump into the terminal. Here is, I'm actually going to minimize all these other ones so that we don't get distracted by everything else that's in this repo. Let's just look at the CrashLoopBackOff. This is the deployment manifest. If you haven't seen these before, it's basically just YAML that is going to define each of these resources. In this case, we're defining a deployment. You can see right here is where I'm specifying that, that app label that I'm using to filter on it. And you also notice all of them are going to have unique app labels here. But excuse me, the main thing that we want to look at is actually this line 20 through 22. And luckily, I already knew that this was the issue, so I have the solution commented out. So what I'm going to do is I'm going to uncomment that. I'm going to save it. So now we're going to be specifying an environment variable whose name is Postgres Password, and the value is the extremely secure password 123. This should at least be enough for us to get past the for the app to come up and to run properly. So let's save that. Let's jump back over to the terminal, and luckily we can just go back through our terminal and run that same command. Again, this is idempotent. So let's just rerun Helm upgrade. Should take a second or two. There we go. You see the revision is now 2, which means we've deployed this twice, which we did the initial install. This is the second one. Now let's do also that same command to go and get the pod and let's see how it looks. Hey, it's running now. So that was as easy as it was to fix it. Now, keep in mind, this is a very kind of trivial scenario. Obviously, there's an endless amount of ways that your application could be crashing, could be going wrong, but all of the debugging strategies there are going to be much more specific to figuring out what is wrong with the application and the container itself. This really wasn't a Kubernetes issue. Kubernetes was crash looping, but it was because the container wasn't properly configured. And so anytime you see a CrashLoopBackOff, the first thing you should probably do is check the logs and see what is going on in your application that's causing it to crash. So we are 1 down. We got 6 more to go. So let's keep it moving. If we go all the way back and we check all of the pods in the debugging namespace, we'll see what the next one is. So the next one is a pod that has a failed ready check. You'll notice here that it's running, but under ready, it says 0 of 1, whereas the healthy pod says 1 of 1. So let's talk about what a ready check is. In Kubernetes, ready means that your pod is ready to receive traffic. If your application is intended to serve traffic, which in this case it actually is, this is a Nginx pod, then Kubernetes isn't going to be sending it any traffic. Only ready pods will have traffic sent to them. This is actually a feature. This isn't a bug. So how is Kubernetes going to determine if a pod is ready? Well, by default, if the containers are all running, then Kubernetes will consider it healthy. In this case, the pod is running, everything is running, but it's still not considered healthy. Now, Kubernetes also allows you a way to specify a more complex and more specific readiness check. Now, the reason this could be important is, let's imagine that your application needs to perform some startup behavior before it's ready to receive traffic. For example, maybe it needs to warm a cache, or maybe it needs to load some data from a database, or maybe it needs to perform a system status check and make sure that all of the systems are healthy. You could have it do all of those things and then notify Kubernetes that it is ready once it's passed all of its checks. So the way you do this is what's called a readiness check. And so let's actually describe the pod, and we'll see if we can get some more contextual information about what's going on. So this is going to be the first time that we're going to be doing kubectl describe. It's exactly the same format as kubectl get. It's just going to be describe instead of get. So we'll do describe. The namespace is going to be debugging. And in this case, the label is app equals failed readiness. Oopsie, I spelled kubectl wrong. There we go. So you'll notice that this is giving a lot of status information. I can scroll up a little bit. This is one of the most powerful commands. This is going to give you a whole lot of information about the status of whatever resource you're interested in. You're going to get the name, the namespace. You're going to get the status of it being running. You get the IP. a subset of some of the configuration data, but the real value a lot of times is actually this events block at the bottom. This is going to tell you all of the events that have been associated with this resource in, I think it's the last hour, maybe it's the last day. It does eventually age off these events. The important thing that we're looking at is this last one right here. There's a warning that it's unhealthy, and the readiness probe, it says, is failing. There's an HTTP probe that's failing with status 404. Now, if any of you guys are familiar with HTTP status codes, 404 means not found. So it sounds like there's been a readiness check that's set up and it's not working properly. Let's actually look at the configuration of this pod and see if we can identify what's wrong. So there's another cool feature of the kubectl get command. So if we type it all back out again, debugging, the label is app equals failed readiness. You can do -o-YAML. -o-YAML means output the YAML version of the whole pod. Now, this is slightly different than describe. Describe is going to give you more status information. This kubectl get -o-YAML is going to basically give you a dump of the manifest as it was configured. So if we scroll up here a little bit, you'll see there's more information here because some of this is computed information that's put in here by the Kubernetes server. But a lot of this configuration you'll see is actually what's in the manifest when we jump back over into the code editor. The main thing I want to look at here is under the containers, under Nginx, we're looking at the readiness probe. And so if we look at it, we're setting up an HTTP GET. What this means is that Kubernetes is going to send an HTTP request to an endpoint of this container on a specified basis. You can see here it's going to wait 3 seconds, and then it's going to do it every 3 seconds afterwards. And it's going to hit port 80, and the path is not real endpoint. Now, this should be the indicator, particularly since we got a 404, which means that the path wasn't found. Probably this not real endpoint is the culprit. This isn't a proper health check. So let's jump back into the terminal and let's fix that. So if we open the failed readiness and we check the deployment, here it is right here. The path is not real endpoint. Let's just comment this out and then swap it over to just the root path. Now, normally you'd actually want to use a real readiness endpoint. A lot of times you'll see /health or /healthz or /ready. Again, if your application actually has some meaningful checks or things that it should do before it's ready to receive traffic, you should perform those things in that on that endpoint before you return the proper status. Now, Kubernetes will treat any status code between 200 and 399 as healthy. For those who aren't aware, the 200s are basically everything's good. The 300s are redirects. 400s are going to be 400s and 500s are going to be some variation of errors. And so if it's a 400 or 500, that means it is not healthy. So I'm going to save that. I'm going to jump over into the back to the terminal. We're going to just go up and rerun that Helm upgrade. And we're going to hope that this fixes it. So let's do the same kubectl get pod. We'll get rid of the -o-YAML. And hey, there you go. You'll see that it's 1 of 1. It is passing the readiness check now. So we have a healthy application now. So that's 2 of the 6 down. And we'll go ahead and move on to the next one. So if we go all the way back to the initial command to check all of the pods, you'll see that the next one is going to be the image pull back off. So image pull back off is actually going to be very similar to the CrashLoopBackOff, except that instead of the pod crashing, it's that the Kubernetes is trying to pull the image that you've specified and it's unable to pull it. Now, this could happen for a lot of reasons. One, it could be that the image is private. It's in a private repository and you haven't specified the proper credentials. And so it's failing on credentials and it can't pull it. You could have network connectivity issues. Perhaps you haven't set up your networking right, and you're trying to reach out to a container that you can't reach. Another one is just a good old-fashioned fat fingering. You misspelled the container name, and it's attempting to pull it, but obviously the container name's wrong, so it can't pull it. So let's go ahead and take a look at the pod configuration, and we'll see if we can figure out what's wrong. So let's do a scoped query here. We'll do kubectl get pod in the debugging namespace. We'll filter it by app equals, in this case, it's image pull back off. Back off. And we're gonna do the same thing, -OYaml. Let's just jump straight in and start looking at the config. So we'll scroll up through this, and we're going to look at specifically the image. We know there's something wrong with the image. And if we look at the image name right here, it's NIGN, which happens to be Nginx spelled backwards. Let's assume that this was just either somebody being clever, which was me, or a fat fingering. This just isn't a valid image name. So luckily, this one looks like a pretty easy fix. We're just going to jump into the editor. We'll fix that and set it over to the actual Nginx, and we'll redeploy and see if that fixes it. So let's open the editor again. We'll minimize this one. We'll open up image pull back off. And there it is right there. We're going to comment out the bad one, and we'll uncomment the good one. We're just going to save it. Let's redeploy. Scroll up here to this, rerun it. There we go. Now let's do that kubectl get again. And hopefully, hey, no more image pull back off. It's actually running now. That was an easy one. That was the easiest one of the bunch. Okay. Let's move on to the next one. So that's 3 down. We got 3 more to go. If we go back through and look at all of the pods that are in the namespace, we actually have this next one. Now, it's in a CrashLoopBackOff, but what we're missing here a little bit is there's some context around why it's failing. And it's really just a timing thing about whether or not you can see why it's actually failing. So let's try to dig in a little bit onto this guy and see if we can figure out exactly how it's failing. So let's do a kubectl describe on this pod and see if there's any hint in the events. So if we do kubectl describe pod in the debugging namespace. Actually, you know what? Instead of doing it this way the whole time, what I'm going to do is you can just specify the name of the pod here instead of using the filter. I've been using the filter the whole time, but you can just specify the pod name here as well if you'd like. So if we describe it, we're actually not seeing it in here either. It's kind of a very specific timing thing to be able to see. Actually, if we scroll up a little bit here, we can see it. There it is. If we look under the containers and we see the last state, there it is right there. It was a little bit hidden from us. We had to dig a little bit to find it. So we see that the pod was terminated, and the reason was because it was OOMKilled. So what does OOMKilled mean? Well, the OOM part of this is out of memory. This issue arises when a container attempts to acquire more memory than it is allowed to. So this leads to a broader discussion about how resource allocation works in Kubernetes and pod scheduling. So allow me to kind of explain this a little bit, because understanding pod scheduling and pod resources is actually very important to diagnosing and understanding application health. So the Kubernetes cluster needs to understand things about your pod in order to schedule it, which scheduling means just placing it on a server for it to run. So in order to schedule it, it needs to know some things about your pod. One of the main things it needs to know is how many resources do you expect your pod to need? Do you need 1 CPU? Do you need 10 CPUs? Do you need a fraction of a CPU? How much memory do you need? The more and the better information you give, the better Kubernetes is going to be able to schedule your pod correctly. Because again, your pod should be ephemeral. They should be able to die and come up anywhere else and be able to run with effectively minimal impact. So how do we tell Kubernetes the resources? Well, there's actually two different ways you can specify resources for. And when I say resources, I'm specifically talking about CPU and memory. Those are the main ones that you have to specify when you're trying to run applications. The two ways that you can specify it are what are called requests, so resource requests, and resource limits. Resource requests are your way of telling Kubernetes, this is my best estimate about how much CPU and memory this pod is expected to consume. You really should try to be as accurate as you possibly can with this number for a couple reasons. One, these resources are going to, in some sense, be allocated for that workload. So you're going to be given access to the resources that you've requested. Number two is when Kubernetes is trying to schedule your pod, it's going to look across all of the nodes, which again, nodes are VMs, in your cluster and say, where are there enough, which node has enough resources to be able to properly handle this pod? And it doesn't do that, by the way, by looking at the current CPU load or the current memory load. What it does is it says, what are all the current pods that are scheduled on this node? What's all of the CPU that has been requested by those pods? And that is how much CPU, regardless of the load. So if you have 3 pods running and each of them require half a CPU, Kubernetes is going to look at that node and say 1.5 CPUs is reserved. And if you only have 2 CPUs on that node, you only have a half a CPU remaining. So if you needed to deploy something that needed a full CPU, it couldn't go on that node. Even if that CPU is actually idling, and so there was technically enough overhead for it to go there, Kubernetes doesn't look at the load. It looks at how much resources have been requested by the pods that are currently scheduled on that system. So this again is why it's so important to be accurate here. If you request way more resources than you need, your cluster is going to be very over provisioned and you're going to have a lot of resources, CPU and memory that just aren't being utilized. However, on the other side, if you underestimate, if you say this only needs 1/10 of a CPU and it's using a full CPU, you can run into a situation that's called a noisy neighbor, where one CPU can start really like pulling a lot of resources from some of the other pods. Now, ideally, if you've set the right resources for each of your pods, those resources should kind of be allocated for them. But you're just going to run into some very weird throttling of your CPU, and it's just a mess. So the main thing is always specify resource requests and get them as accurate as possible. That's CPU request side. The other side of this is limits. Limits are hard limits on the amount of resources, again, both CPU and memory, that your pod can use. If you specify a CPU limit of 1 and your application attempts, it's multi-threaded and it attempts to use 4 CPUs at maximum capacity, Kubernetes isn't going to let it. And in fact, Kubernetes relies on Linux C groups for those that are interested to actually enforce all of this. But what will happen is your whole pod is going to get throttled down to a single CPU. And that's not nearly as bad as what happens if you try to exceed your memory limit. If you try to exceed your memory limit, if you say you can use 100 megabytes and you try to allocate even 101, you will immediately get OOMKilled. The pod will get OOMKilled. It doesn't just halt it and say, no, sorry, you can't. It completely kills the pod. It's because it's much harder to restrict memory access. So instead, it just kills the pod. So for this reason, limits should be used very intentionally and very sparingly in your code. It can be useful if you have situations where you're concerned there's a memory leak, and you can put a cap on it and say, if you do have a memory leak and you get beyond a certain amount, it's just going to kill that pod. And that's much better than your pod endlessly consuming memory. Additionally, you can put some limits on your pods just to make sure that you don't run into a noisy neighbor scenario where they, under certain circumstances, drastically overuse their requested resources. So there's a lot of explanation around resources, but since we're being OOMKilled, that immediately gives us an indicator that we must actually be using memory limits, and we must be exceeding those memory limits. So let's just jump straight into we've already seen how kubectl get can pull the YAML. Let's just jump straight into the configuration, or I should say the manifest in the, in the editor, and we're going to fix it from here. So if we minimize image pull back off and we jump into OOMKilled, first, I'll just show you the little script that we're running in here. It's just a little Python script, and it's going to loop for about 100,000 times. And it's just going to append to a string. And so this string is getting bigger and bigger. Now I've run the numbers, and this thing is going to end up consuming about 50 megabytes worth of memory. And so I know that ahead of time. So let's jump over into the deployment and let's see what sort of limit we've actually placed on this. And you can see right here, here's the resources block. You can see we're requesting 1/10 of a CPU and 10 megabytes of memory. Well, that's not quite right. As I just said, 50 megabytes is actually roughly what it should be using. I'm going to go a little bit more than that and say, let's just update that to 60. And for the limits, let's just bump it all the way up to 100. There's no reason to have a low limit on this thing. You should have it much higher. Usually they say at least 1.5 to 2 times what the request is. So let's save this. Let's jump back into the terminal. Let's redeploy, and let's hope that it can stay up and run. Deployed again. This is revision 5. If I do that same kubectl get pods, well, let's do L app equals, what was this one? I believe it was OOMKilled. Hey, it's running. It's been running for 16 seconds. And actually, if we do a kubectl get logs on this pod, I'm just going to do it like this. -n debugging. You'll see that, I was hoping it would show it. It actually makes it all the way through, must not be dumping the logs. It makes it all the way through and actually says completed at the end of it. So luckily, we have a functioning app there. We're good to go. So that's 4 out of 6. Let's jump into the next 2. So let's go all the way back up, and we'll look at the remaining pods. So hey, this is already looking better. We've got these guys all working healthy. Now we got 2 remaining pods that are in this pending state. So let's talk about, what does pending mean? Well, if a pod is stuck in pending, this is a part of the scheduling process of Kubernetes. So we just talked about how resources play into pod scheduling. What happens is you submit a request for any resource, a deployment, a pod, any of these things. And Kubernetes, specifically in the case of a pod, is going to try to schedule it, which means it's going to try to find a node to run this pod on. Now, there can be any number of reasons why it can't. Maybe you don't have enough compute remaining in the cluster. Maybe your resources are completely wrong and you're asking for more resources than any node in the cluster has the availability to provide. Maybe you've asked for a volume on it that it can't bind properly. Hint, that might be what the next one that we go through is. So in this case, we have to figure out, why is this pod stuck in pending? So in order to do that, we need to dig in a little bit further. So let's do a kubectl describe pod. And again, actually, we'll go ahead and do -n debugging, and we'll do debugging. I got to spell this properly. And we'll do -l app. In this case, it equals pending resources. That's the label of this one. And it needs to be described, not described. There we go. And we're just going to jump straight down to the events. We've kind of seen how this command works before. And this is exactly, we have got 2 very relevant events here. Let's dig into them. So the first one is the scheduler itself. Let's look at what this one says. There are 0 of 3 nodes available to schedule this pod. All 3 of them have insufficient CPU. It talks about preemption. FYI, preemption here is Kubernetes can actually be very smart for you. If you have a high priority workload that needs to get scheduled, Kubernetes will actually evict low priority workloads from certain nodes in order to make space in terms of resources to schedule the high priority pod. It's very, very cool. And again, this is one of those things that this is some of the impressive capability and perhaps complex capability that Kubernetes has, but you don't really need this until you're running a lot of high-end kind of multi-tier of priority workloads. So what it's saying here is it can't find any preemption candidates to evict in order to place this thing either. The last thing that's important is the message right above it, and that's saying that the cluster autoscaler also isn't going to be triggering a scale up. This usually means that the cluster autoscaler has determined, which by the way, the cluster autoscaler is what will add and remove nodes, so your worker nodes from the cluster. It'll do this as you request more and more pods landing. So, but the cluster autoscaler here is refusing to scale up. It's saying that there would still be insufficient CPU to try to schedule this pod, even if it adds a new node. Okay, well, let's dig into why that is. Let's actually describe let's get this specific. You know what? Actually, we don't even have to get it. We can just look a little bit higher in this describe, and we can see the resources that have been requested here. We could get the same information if we did kubectl get -OOMKilled, but we can see that we're requesting 20 CPUs for this workload. Let's hope that that was a fat finger by somebody, because 20 CPUs is a very, very large workload. So let's see what we have in our nodes themselves. So we can do kubectl get nodes. This is going to show us kubectl get nodes. This is going to show us all of the nodes running in the cluster, which right now we have 3 of them. Let's just describe one of these nodes. Kubectl describe node. If we scroll up, you'll see here under capacity, this is going to tell us the full capacity of what this single worker node has. And what you'll see is that it actually only even has 2 CPUs. So this is why, obviously, there's not going to be 20 CPUs laying around on any of the nodes in the cluster. But this also explains why the cluster autoscaler refused to scale up as well. Even if it added 10 new nodes to the cluster, effectively bringing 20 CPUs into the cluster, your pod can't get spread across 20 nodes. It has to land on a single node. And so if we added a new node in this case, we would just add another 2 CPUs and the pod wouldn't schedule anyway. So the cluster autoscaler is saving you money by not adding any more nodes. It isn't going to be able to scale it anyway. So there's some other interesting information here. The number of bytes of memory, this ends up being about 4 gigabytes, and also the number of pods. There's actually a limit on the number of pods that can land on any given node, regardless of resources. In this case, it's 17. That's just some side information. So let's jump back over into the editor. We're going to go into pending resources, into the deployment. And you know what? We're just going to reduce this thing all the way down to 0.1 CPU. There's no reason why, particularly just a little Nginx pod, which is what we're running, needs anything more than 1/10 of a CPU. And as you can see, you can actually use fractional CPUs there, or decimal CPUs. Okay, let's redeploy this. And hopefully we'll see this thing is going to go from pending into scheduled and ready. So let's do pod, and we'll do L app equals pending resources. There it is. It's up and running. There we go. That's 5 out of the 6 scenarios that we were planning to go through. So we got 1 left, and we'll see if we have any time for kind of an extra credit one that we can go through. So if we go back up and we look again at the pods, actually, I can just delete the label here at the end, and we'll see all of the pods that we have in the namespace. And we got 1 more of them here that is pending, and it's pend vol, which should give you a hint that this is a volume issue. So let's go ahead and jump straight into this. If we go ahead and describe this pod right here, if we do kubectl describe pod, by the way, you can use shorthand in some of these. So PO is the same as pod. We'll go in the namespace debugging. And we're going to do app equals pending. I believe it's pending volume for this one. There we go. And again, we just jump straight down here to the events and we see what's going on. Here it is right here. The default scheduler is saying the same thing. 0 of 3 nodes are available, but in this case, it's not a resource limitation. It's that all 3 pods have an unbound, immediate, persistent volume claim. All right, what's a persistent volume claim? I'll try to make this brief because this is a little bit beyond the whole debugging thing. Persistent volumes are Kubernetes' way of having effectively persistent data associated to your workload. So ideally, in most scenarios, your workloads are going to be stateless. And what that means is there's no information that needs to persist, from instance to instance to instance. If one pod dies, move somewhere else, that's fine. You don't need to transfer any data there. However, this isn't going to be the case for things like databases. A database pod needs to store the data because if it needs to move, it needs to take that data with it. This is what a persistent volume is. The persistent obviously means it's going to persist place to place. The volume is just Kubernetes lingo for storage. And a claim is you're making a claim against some volume. So we won't say anything more really about that. What's going on here is that Kubernetes is saying that the persistent volume, the storage that's been requested to be associated with this pod isn't bound. So let's actually dig into the persistent volume claim and see if we can figure out what's going on. So we can do the same thing. Kubectl, we'll do kubectl get. In this case, we use PVC. This again is the abbreviation. You could type out persistent volume claim if you want. We'll go debugging and we'll say the label is app equals pending volume. There it is. And sure enough, its status is pending. Just like a pod being pending, we should dig into exactly why this is. So let's do that same command. Instead of get, we're going to do describe and see if the events tell us exactly what's wrong. And there it is right there, events. And it says the storage class, not real SC, which is a storage class, cannot be found. So what is a storage class? Again, very briefly, a storage class is a way of representing a type of storage that you could use in the cloud. By default, most of the cloud, I think all of the cloud Kubernetes clusters will come with a default storage class. I'm talking AWS's EKS, GCP's GKE cluster, and Azure's AKS cluster. All of them should come with a default storage class by default. So if I do kubectl get storage class, we should see what storage classes are available. And there you go. We've got one and it's named GP2 and it's actually the default. This means if you don't even specify a storage class, you're just going to get GP2 by default. GP2, by the way, means general purpose 2. This is Amazon's. We're running in an EKS cluster, FYI, right now. This is Amazon's. You can see it's an EBS type of storage. Using GP2 is going to create an EBS volume for you. So that's probably the storage class that we want. So let's jump over into the configuration and let's fix it. So if we look in the stateful set right here, which by the way, stateful sets are what you should use instead of deployments when you actually have persistent state associated with your workload. You should always be using a stateful set instead of a deployment. So the old storage class name was not real storage class. I'm going to comment that out. In this case, I'm going to delete the storage class, or I'm going to uncomment storage class GP2. Let's save it, and let's see if we can just run this and things are going to work. So let's go back up to Helm upgrade. And we're going to try it. Let's cross our fingers. Oh, no, it didn't work. So this is actually an important thing here. It failed, but let's dig into why it failed. It says it can't patch this stateful set. And the reason is there's actually a blessed set of fields that can be modified in place. and is saying that the only fields that can be modified in place are replicas, the pod template, the update strategy, the persistent volume claim retention policy, or the min ready seconds. Everything else is effectively immutable. Now, this is important because let's assume that we'd actually deployed this thing successfully. What could potentially happen is we have a running database that has gigabytes of data in a persistent volume, and somebody accidentally changes the storage class. What would happen if it took that update, redeployed it, and now swapped to a completely new storage class? It wouldn't migrate your data with it. Your database would come up completely empty. This would be a kind of you'd have an outage from this. So what we have to do here is we need to actually destroy the stateful set and the persistent volume, and then we can redeploy. Now, it doesn't really matter here because the stateful set doesn't have any data associated with it. So let's go ahead and delete it, and then we'll redeploy, and we'll make sure that it actually works here. So we'll do Helm delete stateful set in debugging, and we'll use the label app equals pending volume. What did I do? Apparently you can't do that with delete. Good to know. Well, I will say, not Helm. Sorry, that needed to be kubectl. No wonder. Kubectl. I'm getting my tools mixed up here. Shoot. Let's do kubectl delete stateful set. This right here. There we go. It's deleted. We also need to delete the persistent volume claim. The reason we have to do this is just by deleting the stateful set, you won't delete the storage behind it. This is, again, a safety mechanism. So if you delete your compute, you don't delete all of the state along with it. Now those are deleted. Let's actually try running that Helm upgrade again. Where was it? Helm upgrade. And this time it should go through just fine. There we go. Let's just do kubectl, get pods and the debugging namespace. And hey, we've got all of them except this last one, which was extra credit anyway. All of them are now running, they are ready, and they are healthy. So there we go. We've successfully diagnosed and fixed all 6 of those. Let's jump back into the slides. I know we're just about at time, and we'll wrap things up. So let's go into, let me minimize, let's see, let me pull this up. There we go. So you've seen now every one of these commands and how powerful they all are. Almost everything we did with kubectl get, kubectl describe, kubectl logs. We'll probably have a future webinar where we dig into kubectl port forward and exec. We just didn't have time to get into that today, and I don't want to take any more than the hour that's been allotted. To recap, so we fixed and debugged a CrashLoopBackOff. We debugged an image pullBackOff. We understood and fixed readiness check issues, and we understood how readiness checks work with sending traffic. We understood resource specifications, and we fixed an OOMKilled. We fixed pending pods due to resources and volume constraints. And I was hoping we would get to fixing a pod that wasn't web accessible, but we'll handle that in a future webinar. That's all I have for you. Here's some extra resources. You can check out our platform where, by the way, we handle a lot of this stuff for you automatically so that you don't have to dig into the cluster like we just did to debug a lot of these things. You can head to massdriver.cloud today. If you'd like to email me directly, that's my email. If you'd like to schedule a demo with our platform, go ahead and hit that schedule a demo link, and we can get you set up. We'll be hanging out here in the webinar for a little bit longer just to answer any questions that you guys may have. But I appreciate everybody who's shown up, and I hope that this was helpful. And we'll see you next time.